Hello. Welcome to our discussion on AC machines here. So far, we have been talking about some basics related to AC machines, and let's extend that knowledge to understand a little bit more into how the magnetics work inside an AC machine, particularly magnetomotive force and the flux distribution inside it. And later, we can look at how the back EMF looks like on such an AC machine. Okay. Now we know we have looked at how torque generation and how the flux works in generating that electromagnetic torque in an AC machine. However, we need to keep in mind that in a practical machine that tends to be a little bit more complicated than what we have seen. What we looked at was a simplified approach of looking at the machines just to get that initial understanding. So this is another step towards that a little bit more deeper understanding. Now, rotor is made up of ferromagnetic material, and of course, we're going to see an air gap between the rotor and the stator. Depending on the size of the machine, depending on the amount of energy it needs to transfer, that air gap will vary. All right. Now, given air and the permeability of that with respect to other ferromagnetic material, the reluctance is going to be much higher in the air. So because of that high reluctance, flux will try to take the shortest path through the material or through the air gap. So given this circumstance, we're trying to understand what would an ideal magnetomotive force or a flux density distribution would look like inside a machine, and then we can now relate that to our practical machine and see how close can we get in terms of achieving that sinusoidal distribution. Okay. All right. So now when we look at a cross section of the air gap, a cross section of the machine, we can see the stator, the rotor, and our air gap. Okay, and then this is a snapshot in time, which kind of freezes what the flux lines would are doing at that instance. Of course, if the motor is rotating, this is going to rotate. Now, for sinusoidal flux density of back EMF, we need either windings or magnets or a combination to achieve that sinusoidal distribution. So let's assume we have achieved that. And if we have achieved that, if you're trying to see if it does result in such a flux density or magnetomotive force, how do we verify that? Okay, so in order to find the MMF, you can either use N times I. If you have a sinusoidal distributed windings, now you can multiply N times I, you can obtain MMF that way. If you have a way of measuring flux, you can count the flux lines and then multiply with reluctance, or you can use HDL, the Ampere's law, to determine how that flux density variation looks like. Okay, so given this distribution here that we have, these flux lines are showing, we have less flux lines here compared to here, and then we see the most change in flux lines here compared to here, and then this is where again, so the flux line goes into the stator from the rotor and returns. So we have a closed loop in that between the rotor and the stator. The flux travels through in that in that manner, and then we can see the flux lines returning. Right, so these arrows are going in, whereas these arrows are going out of the stator, assuming we have a magnetic rotor. Now, in order to see the variation, we'll basically start from here and go around the rotor or around the machine, and we can try to plot what that variation looks like. Okay, and if you follow HDL, depending on size of the loop, we can see that our flux density will peak. And then because of the returning flux, when we extend our loop, so we can start with loops like very small loops, and we can then build the loops up to capture more and more flux. And you can see that after 90 degrees, because of the returning flux, the total flux density, or total MMF, falls, and then it goes to a peak, a negative peak here, and then it returns to zero as we come back into the same location, because whatever the flux goes out has to return. So it has this sinusoidal distribution. So that means in order to achieve such a distribution, we have to have the flux lines or flux density to be a sinusoidal flux density around the air gap. Now, achieving this, what we want is one thing, and achieving this practically is another problem. So if we are to achieve sinusoidal distribution of flux, we'll need sinusoidally distributed windings, but that is impractical. That if you want sinusoidal distributed windings, that means we technically need the windings to be distributed around the rotor in this manner, right? So we need ideally sinusoidally shaped set of windings, so which is very difficult. There are two different approaches that tend to be followed in the industry. You have a set of distributed windings, okay, per phase. So we are only looking at one phase here, and this is a distributed winding, and what that means is different slots have different number of windings. Okay, so 10 here, 10, 7, 3. So we are actually changing the number of windings in each slot to get closer to a sinusoidal distribution as possible. Okay, ideally speaking, if we have an infinite number of slots, we can achieve a very fine sinusoid, but given the cost of manufacturing, we do have to reduce the number of slots, and now we have a finite number of slots with the number of conductors being different in each slot. Okay, and this way, and this is only for one phase, and you can reuse the same slots and add more and integrate your phase B into those same slots, phase C into the same slots. For example, if I take a look at this slot, right? Let me draw a cross section. So I have, let's say, 2, 3, 4, 5, 6, 7 of phase A, and then let's say 3 of phase B. I'm just choosing a random one. So 3 of phase B, and then 10 of phase C, right? So you can have such a combination in that single slot, where as you go around the rotor, you see the different phase A, B, C winding ratio change, but you are using the same number of slots. And if you're sticking to phase A, if you just look at phase A, and if we look at the MMF plot, magnetomotive plot, using our Ampere's law or flux, by counting the number of flux lines, you can see that with alpha, with changing alpha, this is alpha, as you go around the machine, we see discrete variations, because depending on where we consider our loop to be at, right, we'll see a jump. We'll see a jump in the number of conductors, right, and then it'll stay like that, and then we'll see another jump here. So likewise, you're going to see stepwise variation, like a stair-step kind of a variation, and of MMF around the machine, around the air gap. Now, The advantage here is based on Fourier analysis, we know that we have a fundamental with a certain amplitude. The disadvantage is there are certain harmonics associated with such variation. Okay, so because of that, you will see some torque ripple. So depending on what type of a machine you want and what type of performance you are looking at, you may have to change some of these winding distributions to get to achieve optimal torque output or reduce torque ripple in the machine. For permanent magnet machines, there are other methods designers follow. You can shape magnets. So assuming this is your rotor and you have a surface mounted magnet on the machine. So the magnet is mounted on the rotor surface. So this is your, ideally this is your stator. Okay. I'm not drawing any slots there, just showing you what it would look like. So you have your rotor, you have your magnet, you have your stator. And what typical designers do is, in certain cases, they shape the magnets, shape or shave the magnets. So to get the sinusoidal flux or sinusoidal back EMF that they'd want. Okay, so this has to be done very carefully when certain this approach is followed. So and all this is trying to get as close as possible to a sinusoidal MMF in the machine. Okay. So we talked about the distributed winding case. The other approach is basically concentrated windings, which is basically you have two slots dedicated for phase A, where all your windings are in that slot or in those slots. Okay, and then when you go around the machine and when you look at MMF, it's going to look square, like it's like a square. So of course, from the Fourier analysis, we know that this is going to have more harmonics than our previous case. So, but this is still useful to a certain extent if you don't care about torque ripple, if you're not worried about, truly non-sinusoidal back EMF. These machines are also applicable. These can be used. It reduces cost of manufacturing production significantly. Okay, so these are another type of machines that you come across. Now, it's also important for us to understand back EMF and flux density. We'll talk about the phase voltage in a later video, how we need to apply the voltage. However, we know that there is a relationship between flux and the back EMF, right? So we know back EMF E is proportional to the rate of change of flux, which is dBm sine omega t times A, assuming a uniform cross-section, a constant cross-section. Now, when we take the rate of change of our flux density, we can see that we have, so for a sinusoidal flux, we have a cosine back EMF. Okay, so which means your back EMF 90 degrees out of phase with your peak flux location. Okay, and also the amplitude changes with your speed. All right, so this is a waveform showing you the relationship. So if you have your flux density distribution or flux distribution in this manner, your back EMF is going to be in a cosine relationship. It has a cosine waveform which shows that 90 degrees phase difference. All right. The importance here is when you apply voltage to drive a motor, we need to think how we want to align our voltages, how we want to align our currents with respect to our flux density and back EMF. So this is a critical piece of information that we will talk about in one of the videos very soon. Now, again, the back EMF here is for an ideal sinusoidal flux density, if there are harmonics in here, you're going to definitely see harmonics reflect on your back EMF. So you'll see different shapes of back EMFs. For example, you're going to see something like this in certain machines, depending on the design. You might see waveforms like this. So they're not going to be truly sinusoidal. Okay, and in certain cases you might see truly sinusoidal back EMF. I don't want to say truly sinusoidal, but very close to sinusoidal shape in terms of back EMF. Okay, so this is a little bit about how that flux density, MMF, and those are related to each other. And in the future, we will talk in detail about how you choose your voltage to apply, or how you apply a voltage to your machine to optimally drive these types of machines. Okay, thank you.